Yesterday I posted a video that got a lot of attention because it shows there's a focal point of stability between a big ring magnet and a floater magnet that lies above it. Today I'm going to explain the physics and show you how you can do these same experiments at home. There's a ring magnet of 140 millimeters with an 80 millimeter hole. Then we have a 70 millimeter neodymium magnet, and they're all North Pole magnets. And you can see the 70 millimeter magnet is repelled from the central hole, but it's actually attracted to all the outer parts of the magnet. Repel, attracted. So we'll explore more today how that works, and I'll show you the physics, and you can repeat the same experiments for yourself. You won't find this anywhere in textbooks. They don't know anything about it. This is where you have to go to learn about magnetism. As a follow-up to a previous video, we're going to ask, what does it take to create a focal point of stability for a little magnet floating over a ring magnet? Here we have a ferrite ring magnet, a size 145 millimeters with an 80 millimeter hole. In front of it we put a 40 millimeter magnet, and you can see it's repelled, but also it attracts back inward. So that's what we call the focal point. Let's try a series of magnets of larger size to see next what will happen. When we go up to a magnet of diameter 50 millimeters, we see almost the same behavior. It repels, but also it gets attracted inward. A magnet of 60 millimeter diameter shows the same effect. It's repelled from the center of that ring magnet, but also it's pulled inward toward the focal point. Now we'll go up to a magnet of 70 millimeters in diameter, which is just slightly smaller than the 80 millimeter hole. Again, it's repelled very strongly, and also it's pulled inward very strongly. We'll look at a magnet of 80 millimeters, which is the same size as the hole in this ferrite ring magnet, repelled very strongly from the center, but also it's pulled inward. Repel, pulled inward. We'll look at a ring magnet of 100 millimeters, which is actually bigger than the 80 millimeter hole. Now we see repulsion quite strongly, but there's no focal point. It's always repelled outward. So to see a focal point, the magnet, any of these, 80 to 40 millimeters, has to be the same size or smaller than the hole in a big ring magnet. To be thorough, next we'll replace that big ferrite ring magnet with a little neodymium ring magnet of 100 millimeters in a 60 millimeter hole. We put a 40 millimeter magnet near it. We can again see a focal point, repelled, but also pulled inward. And the magnet is smaller than the hole. We go up in size to a 50 millimeter magnet. It's the same thing, repelled, but also pulled inward. The magnet is smaller than the hole. To a 60 millimeter floater magnet, which is the same size as the hole in this neodymium ring magnet. There's a focal point again, repels from the center, and also gets pulled inward. If we go up to a magnet of size 70 millimeters, which is bigger than the 60 millimeter hole in this 100 millimeter ring magnet, then we see repulsion, but it only repels. There's no attraction and there's no focal point. Go up to a big 80 millimeter magnet, which is bigger than the 60 millimeter hole in this 100 millimeter neodymium magnet. In one orientation we only see repulsion. There's no focal point. In the other orientation we only see attraction, and then there's again no focal point. In order to see the focal point for a magnet, the floater magnet has to be smaller than the hole in a ring magnet. Here we have a 100 millimeter neodymium ring magnet with a 60 millimeter hole, a 40 millimeter floater magnet. You can see it gets repelled, but also it gets pulled inward. And this is its focal point of stability. Repel, attract, repel, attract. If this magnet gets larger than the hole, then that effect goes away and we don't see any focal point of stability. The way this phenomenon works has to do whether the ring magnet is made of neodymium iron, ferrite iron, or pure copper. For the ones with iron, there's a repulsion point in the center, And the attractive point for another magnet is very close to the center. His ferrite iron repel in the center, attract very close to the center. For a ring electromagnet made just of copper, we get repulsion in the center as before, but instead of the attractive point being here from the field, it goes further out. The iron shifts the attraction further inward, and that's why we see a focal point for these two iron magnets, but not for that copper magnet.